All right. Hello, everyone. Welcome to the third Analytics and Manufacturing Data Assets Research Project Seminar. We here at IU have three speakers lined up for you. So we'll have Professor Prateek Sharma talk about the data management pipeline, including a demo of the dashboard. That will be followed by Professor Ariful Azad, who will share with us some of the very preliminary findings he has obtained working with students on knowledge graphs and recurrent neural networks applications to analyze the data. And finally, we'll have Professor Alexander Gumennik, who will tell us a bit about his FAMES lab that he directs at IU, spotlighting why is it a good model for a small lab. So without further ado, Prateek, floor is yours.
Okay, thank you. Let me try sharing my screen. Okay, I hope everyone can see the slides. So, good afternoon, everyone. My name is Prateek Sharma. I'm an assistant professor here at IU, and I mainly work on software systems and distributed and cloud computing. So I'm very excited here to talk about some of my ideas and progress in looking at this project from that perspective of cloud storage and cloud systems. So at a very sort of high level view, this is what our data pipeline looks like. Right? So on the left, we have a large number of on-premises sensors that are measuring power, HVAC information, and so on. These sensors are recording and sending the data periodically to the cloud gateway. And all the way on the right, we have data analytics. Right? That is, we want to be able to predict and model and understand all this and make sense of this sensor data. Right? But in the middle, we have the green portion, which I'm calling as a data management layer, right? Which essentially ingests data from this cloud gateway, from all the sensors, either in a real-time manner or in a batch manner, and then stores it and provides essential sort of storage services for the rest of the pipeline for data analysis and machine learning and what have you. So I view this as an essential sort of infrastructure and bridge which connects the physical sensor data with all the intelligence that we can do on this data. So what are the challenges that are specific to this project, in my view? So we have a large number of sensors, and each sensor generates sort of a continuous time series of data with one data point every 1 second or even more frequently. And we have a huge diversity and heterogeneity in the sensors. Some are measuring different aspects of the power infrastructure, HVAC components, and industrial machinery, metrics, and so on. So we have this classic big data problem. We have a large volume, velocity, and variety in the data. So on the right are what do we want from an ideal data management layer for such a system like this, right? So we want to be able to easily ingest, that means take in all this time series data, which is produced by these hundreds of sensors, and it's expected to grow. Right? We want to be able to store this data in a fast, efficient, and cheap manner. Right? So we want to provide a data repository for all kinds of users and services. So we want easy access and APIs to this time series data. Right? Once this data reaches this or is stored in this data management layer, we want to be able to do some time series specific operations on this. Right? So we want ideally to be able to do some quick exploratory analysis and spot some simple patterns in this large amount of time series data that we have, right? Which involves some kind of visualization and some basic time series operations, like dealing with missing data, which is very common, interpolation, filtering, and so on, right? These are very simple, sort of the basic building blocks of time series operations. And we want to be able to do this in the data management layer itself, right? to sort of supplement and complement whatever analysis techniques are there on the right of the pipeline. And a few more things which are again more time series and this project specific, I think, is we need a good system for monitoring and alerting. So if some sensor value, like the power factor, drops below 0.9, for instance, you probably want to send some alert out, right, to some person or some other downstream system. And finally, you want to be able to create some dashboards for different time series data and components to provide sort of the more human in the loop aspects of decision making. Okay, so on the left are the challenges again, and the question is, how can we address all these challenges in an easy manner, right? And so I claim that these challenges exist and have been addressed in sort of my area of work, which is large-scale distributed systems. So large services like what are running on internet websites, they run on hundreds of servers, and for each server, you need to record and upload performance and reliability metrics and store them somewhere, right? So recently we have seen this big increase in interest in what is called as observability dashboards that are sort of software systems that take in a lot of these time series data produced by software and hardware systems and store them and provide and address all the challenges that are there on the left. Okay. So these dashboards are very popular these days. You may have heard of these. Prometheus is a good example of that. Grafana is another open source alternative to it. And there are a huge number of proprietary ones as well, like Wavefront. So, what are the advantages of using sort of existing observability dashboards for this energy insights project? So it has some practical advantages. These systems are very widely deployed, well tested, and sort of highly scalable. They're designed to scale to tens of thousands of metrics and store them in an efficient manner. They're fairly easy to use and extend and deploy, and you can develop a lot of tools using the APIs that they provide. And finally, they also have a large number of optimizations for storing the special type of data, which is time series data. So there's a lot of compression based techniques for reducing your total storage overhead while retaining the access speeds. So the figure on the right shows the typical architecture of these observability dashboards. So they can take a large number of input streams, either as real-time streams or CSV files or simple network sockets. Then they store them in typically something like a round robin database for sort of space efficient storage, and then they can display that. Right. So instead of going into a lot more detail over these things, let me jump straight to a demo. So what we have done is we have taken the data set that was provided to us by Mega AI, and we have uploaded that into our observability dashboard. In this case, we're using Grafana. So let's jump straight to it. All right. I hope that people have seen, you can see some change in the screen. Okay. So what we are seeing here is we're looking at this one metric right now, which is this Op222 facility energy, the KYZ data and the kilowatt hours, right? So this is the sensor and it produces some data, and we are interested in looking at this for, let's say, 1 month duration, right? So this is one of the advantages of a time series database and a dashboard like this is that you can choose what time scale you want things at. So this is what this data looks like, and immediately you can probably spot some interesting patterns. It is fairly diurnal, so the power increases during the day, goes down, is reduced at night. These two low peaks are probably the weekend where these are not operational, right? So you can easily sort of zoom in into a smaller period of time, let's say for a week, and you can observe and you can examine this data at a more fine-grained granularity. So we have noticed that, as is common in time series data, there are missing values, right? So this dashboard, in this case we're using Grafana, also provides simple time series functions for us to use. So for example, I can fill in this missing data via some kind of an interpolation. So let me try that. So I go to the interpolation function, set the time interval for that. And as you can see, this dashboard has sort of filled in the missing data and interpolated that. There are many other functions which you can use for filtering data, for doing exponential moving averages, and a huge number of things that are very common in this sort of time series data analysis. You can do this in a built-in manner. Right? There are also some other interesting things that you can do. For example, if you want to do exploratory data analysis, you may not be sure of, you want to know which are the interesting metrics and what are their correlations, right? So you can do wildcard based queries, right? So here I'm looking at Opto22 facility energy, and then this has sort of these two EMUs and one KYZ meter. And let's say I want to get the net apparent energy for all of them, right? So I simply have a star here instead of selecting a specific one. And let's see what that gives us. So as you can see, this particular metric was valid for EMU1 and EMU2, and this is shown by the green and the yellow lines, right, corresponding to two different things. Again, you can play around with this. For example, let's say I want to look at what is the power, right? So I take the derivative of this because this is the energy. That's a little bit more of a computation intensive operation, but here you go, right? And you can see this also makes some sense. The power does increase during certain parts of the day, and you're not consuming power during the remaining parts. So briefly, what I want to sort of wrap this up with is you can examine a lot of data very quickly in an easy to operate manner. The user interface is quite nice. You can save queries in a dashboard, which allows you to look at metrics of interest at a later time. You can also set up alerts using this, and you can have various alerting mechanisms like email, SMS, etc., based on certain metrics if they go above or below a certain value. And this is all a sort of an easy to use turnkey solution to a large number of challenges that we had talked about earlier, which I think are important challenges in a project like this. So just to summarize, these kind of observability dashboards allow us with some very powerful tools. They are easy to set up. We have deployed this right now on our internal IU servers, and we'll be happy for more users to use this and play around with this. And if they have any specific use cases, we would love to talk and see how it can be quickly accomplished using dashboards like these or extending them. So that's all from me, and I will sort of hand it over to Ariful, who will talk about, on the right side of things, what cool things you can do by analyzing the data.
Thank you, Prateek. If you have any questions, you can either send them over chat at any time or just hold on to them until the end of all the three talks. All right, Ariful. You're muted.
Sorry, can you hear me? Okay.
Yes.
Okay. Thank you, Prateek. So I will take it from there. So Prateek discussed about how to process the initial data, and then I will discuss about how we can model all the devices and analyze them simultaneously. So this is how we are getting the data into multiple files. So for every asset or device that we are getting, we have a metadata file, and that we are getting this data from Mega AI in this format. For example, this is one example: asset ID, and then particular asset, and we have a JSON file, and in that file we have different properties of that particular device. Here is one example. Suppose we are talking about asset name EMU2, which is part of a hierarchy up to 22, facility, energy, and EMU2. And then for this particular asset, this metadata file will say what type of values we can get, what type of time series we can get from this particular device. Here is one particular example. In this device EMU2, we have EMU2 data, then phase C power, and then we are storing phase C peak voltage. This is one example. We have many such examples. For different devices, we have different properties that we are measuring. So this is the metadata side, like how the devices are logically connected. So this file will give us that information. And then for every feature like this, so for example, if we are measuring voltage that Prateek showed, so we have data for several months, and for every month we have a file for each day, and then for every day we have hour file. That means we have data for every hour, and we can go to second, minute, second resolutions as well. And Prateek mentioned that we may have missing data. So from this type of data, we can get two types of information. First is, of course, for every feature, we get time series data. And then for different features and different devices that we have in this particular location, how they are connected, how they are related, so that we would like to analyze them together, total energy consumption of the same building. So in our analysis, we consider both. We consider the relationship among different devices, as well as the property time series data for each of those features. So in the analytical side, we have three goals. The first goal is based on the observation that we have different assets and devices like HVAC, heating unit, cooling unit, and different things. So those things are related. And those hierarchies will tell us something about the relationship as well. See, if different devices are related, we should not analyze them individually. So based on this observation, what we want to do is we want to capture this relationship using a graph or network. This is not like a social network, but we can think in this way. So we have different entities and they are related somehow. We want to extend beyond that. In a network or graph, we just have some entities, nodes, and they are connected by edges or links. But in this case, we have other information like different features of the devices. And for every relation among devices, we have also information about that relation. So we want to extend beyond that by creating a knowledge graph. And in doing so, we will be able to do an integrated analysis of the entire system. So here is an example. This, even for this simple setting that we have, the graph that we have created, I'll show how we can create the graph, but the graph can be very complicated. The relationship can be complicated. This is an example of the entire system that we are analyzing at this moment. The second observation that we have is, this is not a static graph. That means if we create a network like this where devices are connected, but it should be dynamic because we can add or remove new devices. So if that is the case, then we need a storage system. This is not the individual time series. It is about the structure of the connectivity. We need a storage system that should be fast and distributed transactions and queries on the device level. And for this, we decided to use a graph database called Neo4j to store this type of structure, relationship among devices. And if we can do this, then we should be able to support dynamic interactions and query. And here is an example. We created this graph in a graph database, and from that we can see their entities and relationship. And here is one particular query. Suppose if you want to return something, we can just query, give me those devices with this with particular properties. We can query that. So this is our objective two. The first one is how to capture the relationship, and the second one is how to store it so that we can manipulate them dynamically. And the third objective is data is predictable both spatially and temporally. When I say spatially, that means if we observe one HVAC unit in a particular building, maybe we can predict what we may see in another building. So this is spatial predictability. And then temporally, if we observe data in the past 7 days, maybe we can say something what will happen tomorrow. So that is predictable. From our time series, we can see that. So given this observation, what we want to do, we would like to use spatio-temporal machine learning models to predict energy uses and maybe also recommend strategies to reduce energy uses. And this will give us a data-driven way to predict what we may expect in future. So those are 3 goals from our analysis point of view: understanding the structure and across the devices, and enable dynamic analysis, and also apply machine learning techniques so that we can predict other locations as well as other time points. And here is an example. I'll also show this result. We can kind of predict future values. So in this figure, we have blue represent actual values of supply fan flow, which is cubic feet per meter, and cubic feet per minute. And the red one represent predicted values. So data is quite predictable, and we can predict it using simple machine learning models. So if I discuss our goal 1, as I said, we have different devices and different features, and they are related. Here is one particular example. In the top level, in the data that we have 3 different categories: customer group, EMC smart factory, and Opto22. So if I create a hypothetical root node, it will have 3 branches representing these 3 different categories. Then at layer 2, for each of these different categories, we have 2 different branches as well: facilities and smart factory 1. And then for each of this group, we have other categories like energy, gateway, HVAC, line 1, and so on. So we are at level 3, and you can see this is like a tree structure. We are at level 3, and you can follow from the root to different branches. Then we can go at level 3, we have different devices like HVAC or some other unit. Then from each of these devices, we have subcategories like for HVAC, we may have air handling unit, hot water system, and so on. Then we have to go on step deep. And in this data, that is the last level. That means at that point, we can measure values. So for example, here, we can measure air damper output, supply fan speed, and so on. Those are the actual measurement that we are doing. That means this is a 5-level data that we are analyzing now. And the leaf nodes here, in these blue dots, these are the time series data that we are measuring in every second, for example. This is how different properties, different devices are connected in this particular data set. And we can capture this nicely using a reasonably complicated network. And we can zoom in into different sections. For example, again, that is another view of the same graph. And if we want to focus on only one particular unit, for example, one particular customer group and one facilities in that group, and what other devices you have there, like HVAC, energy, and gateway, we can do that. We can zoom in into particular subgraph of this bigger network and then analyze it separately. That is also possible. So we can analyze the data at different granularities. So summary of goal 1 is what we have done so far. We have captured relationship among devices and features using a graph. And that is only from one data set on data source that we have at this moment. We will add descriptions and features of those different entities and relationships to convert this into a comprehensive knowledge graph. That is our next step that we will do in the future. Our goal 2 is how to make sure that we can process dynamic relationships, like new devices or new assets are arriving or getting removed. To do this, we use a graph database called Neo4j. We can use any other database, that is perfectly fine. And in that database, we store a knowledge graph in this way. For every relation, we have head and relation and tail, 3 entities. So 2 endpoints of the relationship and the type of the relation. And using that, we store this in the graph database. And we can do this at different levels because this is a layered data. We have 5 layers. So for example, devices and asset properties, they are connected in this way. And for every connection, we can tag it with the type of the relation. And this can be common across different networks, and that will help us in analyze them in the future. And we can go one level higher. This is the graph database representation of the same data that I discussed in the previous slide. And we can go one level up. This is the 5-layer data. So we can all represent everything in a concise knowledge graph format in a graph database. So to summarize our goal 2, we want to present the relationship among devices using a knowledge graph in a graph database. And creating a knowledge graph in graph database will enable us faster insertion and deletion. If we have new devices coming and going, we can do that. We can query node at a very high level. And we can also recommend things. We can complete the knowledge graph if we have missing information. And we would also do analysis on top of this type of data. So our third goal is, as I said, we are assuming this data is spatiotemporal. It's not only temporal, because if we consider just one particular sensor or unit, that is temporal. But if we would like to analyze them together, this is spatiotemporal data. And that is a future task, of course. We started with just temporal analysis. That means we consider each unit independent, and then we analyze them using some time series analysis model. So at this moment, we are just using a recurrent neural network called LSTM. In the future, we will actually use spatiotemporal models using graph neural network and recurrent neural network together. So here is one particular example. We can analyze any time series, but here is an example for supply fan flow data from HVAC unit. So this data, we are using data from 22nd April to 31st May 2022. That means we have around 1.5 million records. Since it is too much and the resolution is too high, what we did is we kind of average it for every minute. And then the top figure that you're seeing is that minute by minute view. So that means from 1.5 million, if we do minute by minute averaging, then we can get about 34,000 records for supply fan flow. And y-axis is cubic feet per minute. We can aggregate even hourly or daily. That is also possible. But in this analysis, we are just using this one, minute by minute value of this particular feature. Then we use 80% of the time series to train a recurrent neural network model called ASTM, and the rest of the 20% is for testing. So here are some parameters that we used. I'm not going into the details, but after we train it, when we try to predict the rest of the 20% of the data, we can see that the prediction is quite good, where the blue line represent the actual data, the rest of the 20%, and red one represent the prediction. And that means LSTM is doing a reasonable job in predicting this data. We can actually zoom in. For example, this is, we zoomed in on some portion of that time series here. We have 6,000 time steps here in the prediction. The right figure, we have only 200. Once we zoom in, we can see that there is a gap between actual and predicted values. And that is one thing that we'll have to improve in the future, because LSTM is a simple model. We can do better than this. So just to summarize, our analysis has three parts. One is how to represent and capture the relationship among different devices. Second part is how to enable dynamic processing and dynamic querying in the device level. And the third part is how to analyze them using spatiotemporal machine learning models. So we will, in the future, we will be using dynamic knowledge bases. That is one goal that we'll be doing. We want to do multivariate analysis, because the result that I have shown, they are only tiny dots in the leaves, that one time series at a time. But we want to go up in that tree. For example, if you want to analyze or predict here, this will be multivariate analysis, because you have to consider all leaves in that particular subtree or a subgraph. So that is our ultimate goal. We want to do that. And eventually we will develop new machine learning models for spatiotemporal analysis. So that's all from my side. Thank you.
Thank you so much, Ariful. Alexander.
Let me just share the screen. Okay. So I will give a short introduction about FAMES Lab. FAMES stands for Fibers and Additive Manufacturing Enabled Systems Laboratory, which I'm directing, and we have volunteered for the sake of data generation. FAMES Lab is designed for a full closed loop cycle of smart fiber devices, design, manufacturing, system integration, and characterization. And since it has the whole workflow loop within one space, it can very well mimic typical performance and behavior of manufacturing facility. In fact, this lab is built such that it is a small factory. So just to give a little bit of background, what are the fiber devices? Fiber devices are fibers with active functionalities. An example would be a fiber that packages five human senses and stimuli into a fiber form factor. In order to achieve that, we basically need to develop a device integration approach that would take something like an optical fiber, which is an entity made of one single material, glass, okay, and would transform it into some system with active data processing capabilities, such as sensing and transduction and maybe some data manipulation. And in order to be able to do that, we need a manufacturing approach in which we incorporate multiple materials, not just glass, but also, for instance, semiconductors and insulators, with geometry that represents a typical microelectronic or photonic functionality, and the dimensional control on micron or preferably even submicron scale in order to transform fiber into something that performs like a microprocessor. And without going into too much detail, of how we do that, I can just in general tell you that we are developing a proprietary material processing technique that is achieving for fibers something similar to very large scale integration for wafers. And our VLSI for fibers is a combination of material processing techniques that incorporate 3D printing with high temperature sintering and consolidation, and a set of molten phase processing of glass, including the fiber draw, which is a technique that is usually used in order to create optical fibers. Here we use it on multi-material entities, which makes it significantly more challenging. But we do successfully process multiple materials within fibers to create structures that are typical of integrated optoelectronic circuits with dimensional control, doping control, and have demonstrated a library of devices from photoconducting photodetector arrays integrated in parallel, silicon germanium heterojunctions, silicon PN junctions, and also photonic structures like one-dimensional photonic gratings. The span of applications that we intend for it, from bioactive implants such as structurally functional suture fiber with antiseptic function that we have just recently submitted a paper about. We develop in fiber photonics for preparing future or modern computer platforms for integration into Internet of Things. We think that regular fiber optics is not up to speed with the ability to do this. We develop fibers that have sensing and transduction capabilities that mimic microvasculature action or tactile sensing action, and can be incorporated into bioprints for wound regeneration and tissue engineering purposes, and also fibers with classical optoelectronic performance, such as 1D imaging arrays that can be weaved into fabrics and would form large area imaging systems for surveillance, for instance. So that's a very brief introduction into what we do. You might say that the type of devices that we fabricate are quite narrow in terms of area of application. We make fiber devices, so our devices would be applicable everywhere where something thin and long and flexible is needed, like a fiber. But the set of material processing techniques that we use actually define, first of all, production space that is very similar to normal factory. Okay, so Thames Lab is 3,000 square feet of clean room spaces, which house a number of heavy-duty, high-throughput systems, such as dual-sided fiber draw tower that is capable of drawing fiber at up to 100 meters per minute. So we can, produce kilometers of fiber devices in one run. We have additive manufacturing facility, which has a number of production-grade printers, one for polymers, another one for glasses. We have material processing clean rooms with kilns and muffle furnaces and vacuum furnaces and hot presses. And we also have device characterization labs. So it's a significantly large facility which incorporates both production grade and research grade equipment. So as I said, Thames Lab is factually a small factory with a complex hierarchy of workflow steps. to make a fiber device, you need first to process materials that would create the preform, which is the scaled up replica of the final fiber device that you take then to the draw tower, melt it into a state of viscous liquid and draw like a defecant into the fiber, and then you have a number of post-processing steps. We have a broad representation of equipments typical to both R&D and factory flows, which include high temperature, high power furnaces, automated mechanics and hydraulics, different types of electrical, chillers, gases, compressors, vacuum systems, and also sophisticated environmental control that is designed to make this lab perform as a clean room. It is rated to class 100,000, but the air filtration and exchange and humidity control suits class 10,000. So in that whole space of the lab, air is exchanged at least at a rate of new air every minute in the whole volume. We have equipments with disparate power consumption rates and standards typical to production floors. So you would have not just 110 one phase that you would usually see in office spaces. We also have 208 one phase, 3 phase, 208, 408, and even equipments that are built according to foreign standards with dedicated transformers, such as spark plasma sintering hot press that is of Japanese production. So looking at the lab, typical workflow would start from 3D printing of internal parts of the fiber preform using 3D printers. We have one that is a binder jetting printer tuned to work with silica powder. And we have another one that works with polymers, biocompatible polymers. This is for fibers, for polymeric fibers that we make for biomedical applications. You already have here 2 different types of power consumptions. Then we would take that internal part of the preform, or we can also fabricate the internal parts using CNC. So we have additive approach and subtractive approach. Then we take that most internal part, carefully structured for the functionality of the device, to encapsulate or sinter in a larger rod that would be used as a preform for the fiber. We have for glasses, first, after binder jetting, we need to sinter. So we use for that hot press or muffle furnace, those also 3-phase 208, 3-phase 408. Then we encapsulate that in a larger preform with a glass lace. Then we take it to the draw process, and a draw tower is a 27 feet high setup where the process is vertically aligned such that at 3 levels of the draw tower, the fiber goes through different processes. So you start from feeding the preform into the furnace to melt it down, high power furnace. Then the fiber drops down, carrying with it a thin strand, which is the beginning of the fiber. On the lower level, a tractor grabs on it. So you have automated mechanics to start drawing the fiber. Then that fiber goes through coating. That coating is cured by UV lamp. After that, the fiber is monitored for the thickness and spooled on the lowermost level. Then we have a number of integration schemes depending on the use. So we can post-process for optoelectronic performance, or we can start integrating our fibers into biosystems and characterize it for its medical performance. And we can also characterize it for its electronic and optoelectronic performance. So you have a multi-step workflow where every next step depends on the success of a previous step. So you have complex hierarchies of the workflow. Overall, the lab is a building within a building. So we started with an empty 50 feet high barn. Here in the middle, you can see the draw tower. For the scale, this draw tower is 27 feet high. Okay, and around that draw tower, this is high bay area, you have in belts arranged characterization labs, and on the second floor you have additive manufacturing facility, material processing labs, glass lace space, and then on the service floor, this long piece is the air handling unit of the size of a trailer and a half, and then behind it you have chillers, air compressors, pumps. So just to show one slide that exemplifies the process, this is our big ticket item, the draw tower, shot at different levels of height in the draw tower. Process starts from preform melting, which at 2000 degrees glows white. This in the middle is the coating curing by UV lamp, and the rightmost is the collection of the fiber and the reel. So in order to give you an idea of how the lab looks from inside, this link on the last slide takes you to the virtual tour in the lab. I hope you still see the screen.
Yes.
Do you see a website? Yes, okay. So I don't really have much time, but basically we created a full 3D scan of the lab where every piece of equipment has a pin, okay? And if you click that pin, it will take you to the respective piece of equipment with all the explanations about various types of equipment. So chalcogenide glass evaporator that we have, all kinds of 3D printers that we have, with the videos, with manuals, with explanations of what's the purpose of that setup. So for instance, I want to skip to where the draw tower is. This is our CNC space. It's the dirtiest piece of the lab. Okay, so those are various components of the draw tower. From the bottom to the top, collection reel, draw capstan and computer, optical lab, second floor of the draw tower where the tractor is, working spaces, collection reel of the polymeric fiber, and furnaces, working spaces around furnaces. So yeah, it's a full dollhouse where you can go through, like in Google Maps, and look at different pieces of equipment. So if you just take a tour, okay, those are, for instance, our 3D printers. So we have a large Fortus for printing polymers, and we have X1 Innovent, which is a binder jetting printer, which we use to print silica glass. And in material processing space, the most power consuming piece is this SPS hot press. And you can see, how it is built. It is built such that you have two separate machines. One on the right is just the power supply of that hydraulic press, which punches are heated up by the RF emission that is supplied from this power supply. So that system, for instance, has two feeds. One is 3-phase 408 that feeds the power supply, and another one is 3-phase 208, which controls the hydraulic press and the controls. So you have here the chamber of the hydraulic press, vacuum controls, water manifold, so you have internally cooling water flow and gas flow. So I guess that's kind of it.
Thank you, Alexander. All right. So I think we have about 10 minutes for Q&A and any open-ended discussions. Questions?
Vikram, I have a quick question for Ariful.
Please.
Ariful, how did you do that 80-20 split on prediction and training or test and train?
So, okay. So we have around 30,000 time steps.
Mhm.
So first 80% of that will be part of the training. And the last 20% would be the testing set.
And so when you showed us that graph, is that only on the test set?
Only on the test set, yes.
What does the train set look like? Do you have a graph of the train set as well?
Yeah, so let me quickly share the screen. Yes. So this is the entire time series. This first part is the entire time series.
Okay.
So 80% of this is training and last 20% is for testing. And then this here, I'm just showing the testing part because this is like a zoomed in version. That is why it is.
I understand. Yeah. Could you show me the previous slide again? So these are 5 peaks here that we're looking at. So 5
Yes.
peaks.
And we removed the missing values. So there is no missing value there.
Okay. Thanks, Ariful.
Thank you.
Other questions?
I can keep walking the people through the lab if you want.
So if there is no question, we can briefly discuss, since we have listened from Purdue and also from Notre Dame. So we can see some opportunities of collaborations. So we can discuss that if there is no question.
Mm-hmm.
For example, in my analysis, I'm not sampling. I am actually aggregating information. So we can discuss what is a good downsampling strategy for this type of data.
Well, first of all, Alexander, you have a very impressive lab. So I think we are all just looking at the lab instead of thinking about questions.
Okay,
So,
I will stop sharing.
No, you can keep sharing. This is actually a very good background for our discussion. But as far as collaboration is concerned, I think we'll be happy to collaborate. I mean, this is exactly why we are getting together, not just show off what we can do, but find potential collaboration opportunities. So, I mean, I would love to, for example, just come and tour this lab. It looks really impressive. So hope that's an invitation. But
Yes, it is.
Wonderful. Wonderful. Thank you. I'm sure our Engineering Innovation Hub people would love to see this because they have some of the same equipment, and then I think some of it, of course, is different. So maybe there is some potential collaboration on, using equipment. We can talk about that as well. But as far as collaboration on data concerned, we'll be very happy to. So when you're talking about not some, I mean, sampling and not, oh no, I mean, you said aggregating, not sampling, right?
Right.
Okay. So what did you want to do with sampling the data, or what was your suggestion for collaboration?
Well, sorry, I not suggest. So the analysis that I showed, they're very preliminary. We have not thought about it, to be honest. Since we have about 30 time step per minute, we thought it is too much. So we just aggregated them to create 1 point per minute. But it can be something different. We can discuss and find a solution jointly.
Well, this is actually the route that we took, and that's what I was talking about last week. I think we can discuss the different approaches. One of the problems that we have with EMC2 data is that the data sets are incomplete. We have a lot of data that are missing, and we don't know why. So when the data are missing, when we have those pockets of missing data, in some of the data sets, those pockets are as long as 21 hours, at least on the data sets I've looked at. I don't think we can talk about any reasonable strategy of data analysis when we don't understand why the data are missing. Did they turn off the machine? Did something happen? There was such a major spike in electricity that just everything shut off and the equipment stopped working. So we don't know answers to this question, so we don't know what we don't know. So I'm thinking that one of the questions that we will discuss is the sampling interval, but probably when we have our own data. Right. So Notre Dame is hooked up and we have data loading right now into AWS. So as soon as we have halfway reasonable data set, we'll be happy to share it with you guys. So you can look at the data set that is complete, or where if we have interruptions, at least we'll have an understanding why. Until you have your own data that you can work with, we'll be happy to share ours. Okay. And then we can have a separate seminar discussing those different data sampling techniques.
Okay, thank you.
All right, I think we have about a couple of minutes remaining, and thank you, Prateek, Ariful, and Alexander for nice talks. I think we can end it here, and we'll have the next monthly seminar in October. And thank you all for joining. See you.
Thank you.
Thank you, Vikram, for organizing.
Thank you.